For this lesson, we are going to be taking a look at the second derivative to see what that tells us about the function f of x. And you can see from the title, there are two things that we're going to be talking about here, and it's the concept of concavity and special points, critical points known as points of inflection. So the first thing I need you to remember is the kind of the easier one when we talk about derivatives. The easier one to relate back to the original function is f prime of x, the first derivative. And the first derivative describes the instantaneous rate of change or the slope of the tangent to any point on the original function. If f prime is the instantaneous rate of change of f, then it stands to reason that f double prime is the instantaneous rate of change of f prime. In other words, f double prime describes the instantaneous rate of change of slope, of the slope. How is the slope changing? So the first derivative tells us how the original function is changing, whether it's increasing or decreasing. That's what slope tells us. If we end up at a slope of 0, that means that the function seems to have leveled off, and quite often that occurs at a local extrema. Now I'm going to show you examples where that's not always the case, but that for extrema that will happen. The second derivative tells us how the slope is changing, but we don't really care so much about how the first derivative is changing, even though technically the second derivative describes the instantaneous rate of change of the first derivative. We want to relate that all the way back to the original function, which is f of x. And the way that ends up showing up is in a concept known as concavity, which you might also think of as curvature, but the technical term is concavity of the function. So we're going to use the second derivative to relate back to the original function in terms of concavity. Now, I have a GeoGebra demo that goes along with this lesson, but I've actually done an entire separate tutorial just based around this demo. So I would encourage you to go ahead and take a look at that. It'll be linked, of course, on my webpage, and if I remember, I'll put a link to it into this video as well. Now, I've taken out kind of the highlights of that, and I've captured them on the next slides. Now, it is not my intention for these slides to go into your notes because it's going to be a long lesson as it is, but I wanted you to have the opportunity to kind of see what the highlights were. What was I trying to get across there? So let's start off with this shape. It's actually a parabola, but it could be part of a polynomial as well. But from this curve, the blue, which is f of x, we can see that we start from A, and as we move from A to B, it's decreasing. Then when we reach B, it's at a minimum. And then as it continues from B to C, it's increasing. So the behavior of f of x is something that you should be quite comfortable with right now as far as these ideas, decreasing, minimum, increasing, etc. Now, what is the slope doing on this first interval from A to B? Here you can see the slope is a negative number. At B itself, which is where we had our minimum, the slope is equal to 0. And a 0 slope indicates a critical value. And then as we pass B and we're on the interval from B to C, we have a positive number. So the slope went from a negative to 0 to a positive. And so what that means is if we think about numbers, a negative number, let's say this is a slope of -3. Here we have 0, and here we have a slope, and I won't, just to make it not symmetric, let's say it's 2. Well, if I gave you the numbers -3, 0, and 2, what would you tell me is the rate of change in those numbers? How are those numbers changing? And those numbers are increasing. Sorry, I shouldn't say that. These numbers are increasing. So what I should be saying here is that f prime of x is increasing. And if f prime of x is increasing, what does that tell me about f double prime of x? It tells me that it is positive. And it's positive throughout this entire graph that I'm showing. So the second derivative is positive because the slope is increasing. But what we want to tie that to is the shape. So let's look at the shape here. Here we have, if this was just a parabola, we would call this a parabola that's opening upward. That kind of has a similar term. We call that concavity. So we would call that concave up. And this one would also be concave up. We quite often will call that CU. And this one will be concave up. And then the last relation that I want to make here is between here, the critical value, and here, concave up. If we have a critical value at B, but we also know from the second derivative that it's concave up at B, the only way for that to happen is for it to be a minimum. So we can use the first derivative to tell us whether or not we have a maximum or a minimum, but we also can use the second derivative. And quite often it's actually going to be more convenient to use the second derivative to do that, because we just have to take this value b and we sub it into essentially f double prime of b. And if we find that f double prime of b is greater than 0, that means it's concave up, which means we have a minimum. This is a lot to take in, and I understand that, but I'm going to continue through this, and of course you can come back and look at things again if you need to process this a little bit more. Okay, so I'm going to go through this one in a little bit less detail. I just really want to reinforce what we were looking at. So here I have the original functions increasing, maximum, and then decreasing, which means I have a slope that starts off positive, goes to 0, and then becomes negative. So what would you say about a sequence of numbers, for example from the slope, that started off positive, went to 0, and then ended negative? We would say that these numbers are decreasing. The instantaneous rate of change of these numbers are decreasing, and so that would mean that in all three of these cases my second derivative is negative. And because the second derivative is negative, if we look at the shape, what does that correspond to? It corresponds to concave down, which we will quite often just do capital C, capital D to represent concave down. And as before, I would draw your attention to the idea that we have a critical value and concave down. The only way you can have a critical value here and concave down is if it's a maximum. Now, here are some more unusual shapes, but we do see these in our graphs of polynomials. So in this case, what do we have happening? We have and I'm just going to focus on the slopes now. I have a positive slope. I have a 0. Sometimes this is 0, but it's not always 0. Sometimes this graph can look more like that. So it doesn't have to go flat there. Sorry, there we go. So we have a positive slope, we have a 0 or a slightly less positive slope, and then we go back to a steeper slope. So for example, this might be a slope of, let's say, 3, and then a slope of 1, and then a slope of 2. So we went from positive slope, and we stayed positive or 0, and then positive again. And as you can see, this is not a maximum or a minimum. What is this? This is, if we think about concavity, this part with its positive slope is concave down. This part with its positive slope is concave up. Well, how did that happen? Because here I went from a slope of 3 to 1. It was decreasing. And so we ended up with concave down for the second derivative because the slope was decreasing. Here I went from 1 to 2, which is increasing, which is why I get a concave up. And so the result here is what's known as a point of inflection. And when we switch from concave down to concave up, the way we know that is the second derivative is going to be 0. So this is going to tie in to how we find a point of inflection. The second derivative is equal to 0. I have a similar situation here. In this case, you can see I've got concave up. Over here, I have concave down, and the only way I can travel between concave up to concave down is if the second derivative is equal to 0. And so once again, we use that second derivative to determine where we have a potential point of inflection. And then we take a look at the concavity to see whether or not whether that makes sense. So I'm just adding those extra pieces to try to really emphasize that idea of a parabola, which you should be familiar with. Okay, now I've got a summary table here, so you might want to pause here and take a closer look at this table that I've provided, but I'm not going to linger over this for too long. The one thing I think I'll point out to you is that when we are testing either the first derivative or the second derivative for 0, really all we're finding there are critical values. So that's why I've made this box apply to both first and second derivative. If we find an undefined value where f of a exists, so if the original function is undefined, that just means a vertical asymptote or a hole. But if f of a exists, so meaning if this is not the case, but we end up with an undefined first or second derivative, we may still have a critical value. We just might have something like a cusp, or we might have a special kind of point of inflection that goes vertical at that point. And if we had a vertical slope here, that would explain why we have the undefined. Okay, moving along. Find and classify the critical values for this particular function. It is an order 5 polynomial. And I just remind you here, polynomials don't have any asymptotes, so we don't need to worry about that. We don't have to look for horizontal or oblique asymptotes. So this ends up being a simpler option out of the different options we could have. A polynomial is generally going to be more straightforward. Now, in the name of time, because when it comes to, for example, taking the first derivative, f prime of x, and the second derivative, f double prime of x, at this point, that's simply mechanics. I'm not suggesting it's easy, but it is something you're expected to have practiced and to have become relatively competent in. So I'm going to go ahead and provide those, and I've actually provided them in a factored form. So you wouldn't arrive at these directly. There's some work to be done there, but again, the idea of factoring, for this second derivative, getting it to this form is one thing. You wouldn't really be expected to put it in this form until you were actually testing for 0. So until you get to the point where you're going to be setting these to 0. So here, set f prime of x equal to 0, and here set f double prime of x equal to 0. When you get to these points is normally when you get serious about factoring. I'm going to use the result of my first derivative to perform the first derivative test on these values. So I'm going to be interested in these values. And then I'm going to perform the second derivative. I apologize, that should be a double prime there. I'm going to perform the second derivative test on the values. Well, they're going to be the opposite signs for here. I'll show you what I mean in just a moment. So, first derivative test. So I want to create an interval table. You could do this other ways, but an interval table is probably the most methodical way of doing it. And it's usually a good idea, if possible, you want to line these things up, and you can see I've ordered these, and I want to do my intervals. So for example, this is -2, -1, 1, and 2. I need those to be in order. And if you wanted to, instead of writing these at the top, you could also just record the interval here. So this would be -infinity to -2, and it's an open interval. And then -2 to -1, -1 to 1, 1 to 2, and 2 to infinity. Quite a few intervals there. Then I go ahead and I fill in my values. So when I'm at like a -3 here, and this is the value of putting these in order, because I know -3 will make all of these negative. 4 negatives results in a positive, which means I'm increasing on that interval. Then I do about a -1.5, which is going to give me a negative, a negative, a negative, and a positive. And so that ends up being a negative, which means I'm decreasing. Now, I really want you to be honest about this, because you never know when things can change. But in the case of polynomials, these are always going to be switching. These are always going to be alternating. So, for example, this x minus 2 is going to be negative until we get to here, and then it's positive. This x minus 1 is going to be negative until we get to here. X plus 1 is going to be negative here, and let's see, sorry, where are we here? 0, so that's now going to be positive. And then we have this one is positive across. And so you can see here I've got 4 negatives, then 3 negatives, then 2 negative, 1, and then all are positive. So this is going to be positive, this is going to be negative, this is going to be positive, which means increasing, decreasing, increasing. And so what does that tell us as far as results go? It tells us that if we are increasing and then decreasing, then that means that x equal -2 is a maximum. Here I'm decreasing and then increasing, which means I have a minimum at -1. Increasing then decreasing, I have a maximum. And here decreasing to increasing means I have a minimum. So this is a minimum at -1, a maximum at 1, a minimum at 2. So this is the first derivative test, where I look at changes between increasing and decreasing based on the first derivative to classify my critical values. The next thing I want to do is look at the second derivative test. And so for the second derivative test, the values we're interested in are 0, positive root 5 over 2, and negative root 5 over 2. Now, just as an aside, I've just already calculated this. Square root of 5 over 2 is approximately approximately 1.58. So this one's going to be negative 1.58, then 0, then 1.58. And of course, you could write that as, actually, maybe more properly here. Remember, an interval table is something you're doing really for yourself. But I think I prefer to write it like that. And then I could also write these as intervals. So this would be negative infinity to negative root 5 over 2. And this would be negative root 5 over 2 to 0. 0 to root 5 over 2. And root 5 over 2 to infinity. The reason why we want this is actually when we're subbing in some values, unless you have been very careful about setting these up. Because if you've been really careful, then I actually know this one will be negatives the whole way down, because everything to the left of negative root 5 over 2 is going to make each of these negative as well. And so we end up with the overall is negative. And so what happens when I have a negative result? What kind of concavity do I have when the slope is decreasing? And so that's going to look like this, which is concave down. From negative root 5 over 2 to 0, I'm going to have a negative here. I'm going to have a negative here, but this one is actually going to be positive. So the overall is going to be positive, which means I'm going to get concave up. Here, I still have a negative, but now I'm into positives for both of these. Multiply those together gives me a negative, which is concave down. And finally, I have here, they're all going to be positives. And so that means my product of them is going to be positive, and that's going to be concave up. And so now, when it comes to classifying, what classifications does this help me do? It classifies here. It tells me that at x equals negative root 5 over 2, I have a point of inflection because I'm going from concave down to concave up, so it's going to look something like this. Here at 0, I'm going from concave up to concave down. It's going to look like that, so I have a point of inflection. And here at x equal root 5 over 2, I have a point of inflection, and now I've got concave down to concave up. So I've got those features, and I have the features from before. Now the other thing I want to point out, between negative infinity and negative 1.58, we know we're concave down. But if we go back to the previous page, well, negative 1.58 is between here and here, isn't it? So this value, negative 2, if we put negative 1.58, it would be somewhere around there. So that means at this point, along this line, we were concave down, which means concave down means that, which means x equal negative 2 has to be a maximum. So the second derivative could have told us that as well. The same thing is true here. At this one, we would have found concave up, which means that one's a minimum. And here we would have found concave down, and here we would have found concave up. And so the second derivative can also be used to test for whether or not you have, it's not just for points of inflection, it also lets you find extrema. I couldn't put all of those onto a single table simply because I had so many critical values here. So it made sense to use both the first and second derivative tests for this. But I wanted you to see that the second derivative test also can be brought in and used to help us with finding extrema as well as points of inflection. Okay, that's it for this lesson. There's a lot there to get your head wrapped around, and as I said, I went through an entire demonstration using a dynamic GeoGebra applet that just looks at all of these changes, looks at changes in slope. The first derivative test looks at changes in, looks at changes in the function, which is slope, and the first derivative test looks at changes in slope, which is the second derivative, and concavity.